She started like 6 months before me, and we didn't realize that. Well, it was actually a coworker that I had seen email and she like forwarded that to me and she said, "You like this?" And I was like, and then I read it. I did it. Didn't pick up on the point.
We have like after the
He's the reason I came here. So did I tell you a story about how I highlighted the map of the United States? I took it to him and I said, these are the states where we live. Where should I go to wrestling? He put X's on it. And then I Googled where all the X's were and applied to those schools that just had University of Oregon. So
So I was doing that system in Durham University. It was free internet in 1991, so I was just purely a little I actually almost even by class, and it was just fly on notices all so I applied to 5, so which were randomly there. University of Calgary, Cornell University, one was Ohio State, then USC and UCLA, and got rejected from 4 USC.
there you go. So we actually he tried out being they were all yeah, let's do
All right, thank you, Morgan.
Morgan, are you going to grad school?
Yeah.
Where?
Well, I'm going to take a year off, but I do intend on going to grad school for sure.
Okay.
Any ideas of where you'd like to go?
UW in Seattle or U of O. Those are some pretty appealing places.
And how about you?
I also intend to go to grad school. I haven't decided yet if I'm going to take a year off or not yet. But yeah, I've explored like a number of schools, and I'm from Los Angeles, so schools in that area or in the Portland area too.
Yeah, thank you for both of you for joining us this evening. We really appreciate it. We're happy to celebrate your receipt of our scholarships this evening. So, yeah. Anna, I think we're pretty much ready to get going. You can leave your mask off as the presenter, right?
Okay.
I'm just sort of fidgeting with mine, so yeah.
Since you guys know who I am now.
Yeah, so it's my great pleasure to introduce our speaker for this evening, Dr. Anna Oliveri, right now at Southern Oregon University. Anna and I started our PhDs in the same year at U of O. And another interesting connection to the Portland ACS is that Anna took organic chemistry with Dave Reingold at Geneva.
He's also my advisor.
He's also your advisor. Okay. Yeah, so please join me in welcoming Dr. Anna Oliveri.
Is there a place you want me to stand
Nope.
for the
Yeah.
video?
No, you're fine where you like. Yeah.
I'm supposed to put this microphone on, but I don't really feel like I need it, but for the video I'll wear it. Okay. You're all staring at me. The pressure. Okay, can you hear me better? Okay.
Yes.
You have a pocket. All right, so I am here to talk to you about the characterization of aluminum nanoclusters in aqueous solvents using proton NMR. And so I have some models that as I go through, I will kind of help to show you in the three-dimensional, and I'll pass them around if anybody wants to look at them as well. And so I'm currently an associate professor at Southern Oregon University. I got my undergrad degree at Juniata College in Pennsylvania. I got my PhD at the University of Oregon in Eugene. I did my postdoc at UC Davis, and I'll talk a little bit about some of that work. And then I've been at SOU since 2016. And I'm most likely going to be chair next year, so if you have to contact SOU, I'll be the person in the chemistry department that you will be emailing. And so I just have here some of the work that I've done throughout my career, and I've been lucky enough to have my art featured on the covers of the three on this side are my art featured on the covers of the magazines that my publications were in about these nanoclusters in solution. And so I've studied gallium, aluminum, uranium, and what I'm going to talk to you today, which we can do at SOU, is the aluminum work. Okay, so aluminum is the third most abundant element in the Earth's crust, and it is the most abundant metal, so it's very ubiquitous around. We use it for lots of things in our everyday lives. The metal and also the cation are very important, and so I might use this mouse. Can you guys see that? No, as a pointer. I'm not sure how to. Here, can you see this laser pointer? Yes. Okay, so here's our aluminum, third most abundant element here in the Earth's crust. It's in cosmetics. We can use aluminum as a mineral mimic. It can be used in water treatment. We have it in antiperspirants. There's aluminum in spacecrafts because it's such a light metal, and so you can see that it kind of comes up everywhere in our lives. I'm going to move that laser pointer out of the way when I'm not using it. Okay, so aluminum, when it's in solution as the 3+ cation, as we change the pH, we actually have our species that will change. So at our lower pHs, we have monomers, aluminum 3+.
It's a weak acid, and so it tends to throw hydrogens off and have hydroxides around it in its solvation sphere, and we might get a hydroxide or two forming. But what's going to happen is it's going to start to polymerize, and we're going to start to get these small polyatomic ions in solution before it crashes out around pH 6 as our aluminum hydroxide solid. And then if you go even higher, it'll start to redissolve into basic solution as well. But I am looking at this here, this polyatomic ion, and in reality, let me see how that's going to work. In reality, there's not just one polyatomic ion that forms there. So if we go from our monomers across to our extended networks like a mineral or maybe a thin film, something like that, in this intermediate range, there's not just one cluster that exists, but there's many. Here's an aluminum 8 cluster, 2 different versions of a cluster that has 13 aluminums. Here's an aluminum 32 that is, a polymer of some of our smaller ones starting to stick together. And so it turns out that it's not just the pH of the solution that affects the species, it's also concentration and most likely the counterions that are in there. Balancing out the charge, because these are large polyatomic ions, they're cationic, and so we need some sort of anions in solution to balance that charge out. So at SOU, we're a primarily undergraduate institution. I work with all undergrads. We do have master's students in some areas, but not in chemistry. And so all of the work that I've done in the last 6 years at SOU has been done with undergraduates. I am really interested in just fundamental chemistry and getting in with the students and having them learn techniques and start to do experiments. But we have capstones, 2-year capstones, that our students spend a year doing literature reviews, getting ready, and then they spend a year in lab with me. And so they always have some sort of background lens, a reason that they're doing the research. And so you can see I've had students look at water treatment and the flocculation that occurs, fracking slurries, and using our clusters as mineral mimics to see how the components of a fracking slurry might interact with the mineral surface as it's underground. Environmental stressors on aquatic species, what happens when these clusters are the species in the acid mine drainage compared to monomers. Antiperspirants are a really big thing, and I'll talk more about that as we go. And then recently, vaccines have become so important in everybody's lives, and it turns out that there's aluminum in them as adjuvants in the vaccines. And so some of my students have decided to say, hey, how does that relate to nanoclusters, and look into that. And it turns out the size is a little different, but I allowed them to go down that literature project there. So this is one of my students, Anson, working under the NMR. So at SOU in organic chemistry, they all learn how to use the NMR. They don't usually get under there and tune it the old school way, but this is a very old NMR, so my research students learn how to do it that way. And so they get that experience, and they love taking these type of pictures for their slides, for their presentation.
How big is that?
400 megahertz NMR, and we just submitted MRI, NSF MRI grant to try to get a new NMR because that NMR has been working at SOU longer than I have been a chemist officially. And so we would really like a new one. So I will tell you that a lot of this data, someday I plan to have a new NMR, and this is very preliminary data that I have here. Okay, so in my PhD was when I first got introduced into these cationic nanoclusters. I worked for Darren Johnson at the University of Oregon, and I worked for the Center for Sustainable Materials Chemistry. That's what my funding was through. And so we had this precursor. Now the one I worked with in grad school was a gallium-indium cluster, and now that's right below aluminum on our periodic table, so it has very similar properties. But that cluster could be turned into thin films, very dense, defect-free indium gallium oxide thin films that they could be put in devices. And so my PhD, I really looked at those solutions. They would dissolve these clusters into solution, and then the question was, well, do they just dissolve? Do they fall apart? Do they aggregate? Is there some sort of rearrangement to a different cluster in solution? And so that's what I studied. The aluminum there's a similar cluster here, our aluminum that's a flat, same kind of form. It can be also dissolved into water and spun into a very dense defect-free aluminum oxide thin film. So that's why in graduate school we were looking at these, and the projects were based around that process of taking small pieces and making an extended network. But what I was really interested in, instead of taking the small pieces and building them up, was from the other standpoint, the geochemistry standpoint of minerals weathering. So having these extended networks, and instead these clusters are probably intermediates as those rocks and minerals weather. And so clusters exist as we're building up extended networks, or maybe as we're breaking down extended networks, in addition to just forming in solution naturally. They seem to just self-assemble at the right conditions. So to talk a little bit about some of this background, one area that aluminum clusters are really prominent in literature and application is water treatment. And so when you have pollutants, organic pollutants with probably negative charges on them in solution, you have flocculants. Now those F's are not fluorines, do not be tricked, those are flocculants, right? So these flocculants come in, there's some sort of charge interaction, and then they precipitate out of solution. You have this sludge, but you have this nice clean water that then you can filter away, and that's one way that water treatment is done. When you have the monomer aluminum, it has a 3+ charge, but our polyatomic ions, our clusters, have 15+, 7+, 18+ charges on these polyatomic ions. So this aluminum 30, or this large polyatomic ion here, is a really great water treatment starting material because it already has this huge high charge, and it's going to very quickly pull a lot of things out of solution. Antiperspirants is another area that this is really relevant to our everyday lives. If you look on almost any antiperspirant, unless you're getting aluminum-free antiperspirants, which are really deodorants then, not antiperspirants, it might be small for you to read. Actually, I think you can probably read it. Aluminum, zirconium, trichlorohydrex, glycine. So we got aluminum, we got chloride, we got glycine, and most of the time they put some zirconium in there too. So solid state NMR has been done on just antiperspirants, and they've seen that there are these aluminum 30 units in there. So we have a nanocluster kind of in that solid. And then they've also looked at how these clusters interact with sweat as it flows by a pore. And so you can see people are already studying these clusters and how that impact is. So you put the antiperspirant on, the aluminum kind of dissolves into your sweat, it gets into your pores, which are slightly more basic than your sweat might be, and then all of a sudden it precipitates, clogs your pore, and you can't sweat, right? So that's kind of how that's working. And again, as we're going from something dissolved in solution to something precipitating out to clog your pore, we're most likely having those nanoclusters in there. I always tell my students at this point, this is why I wash my armpits with face wash, right? So like clean my pores everywhere that they're getting clogged. My students love that. Okay, so that's the background. Let's talk about these clusters a little bit more. The first aluminum cluster, it was the first to be discovered. That doesn't mean that it was the first to ever form out in nature, but the main first aluminum cluster, I'm going to call the epsilon aluminum 13. It is also sometimes referred to as the Kagan cluster. A man named Kagan in the 1920s was the first to discover this kind of shaped polyatomic ion, but it was with tungsten. Okay, so they call it the Kagan series. We're going to see a series of isomers, and they're named after him. But the first crystal structure was done in 1960 of this by Johansen. So here is our cluster. I have two different formulas written here for you. We're going to kind of step through the top one, but then I'm going to start using the bottom one, which is a little bit more condensed. So we have this center aluminum here, which is tetrahedral. Okay, and so it is bound to 4 oxygens that are also each tetrahedral, mu4 indicating that it's tetrahedral bonded to 4 things. And then those 4 oxygens each come out to a triameric cap. We have 4 of these triameric aluminum caps on the outside. And then overall it has a +7 charge. So I'm just gonna put all of those polymeric caps all together. It's just gonna be aluminum 13, hydroxide bridges, oxide bridges, and then waters around the outside. And that's kind of how you'll see it from now on. This is studied in the solid state using XRD. You can get a single crystal or you can get a powder pattern and tell that you have it. And then in solution, the primary way that people in the literature and historically have studied these is 27 aluminum NMR. But you can use small angle X-ray scattering, you can use DLS, you can use ESIMS, but there is some controversy about taking a very high charge cluster and blowing that apart in the mass spec and then actually being able to see what was really in your sample versus what you created during that process of analysis. So I would say it's not the best technique, but people in the literature tend to use it sometimes. So in 2002, this cluster was found in nature for the first time. So they took some flocculants from a stream in California and they tested these with solid state NMR and then they dissolved it into solution and they were able to see that this cluster is just naturally forming in this stream. And then there's this beautiful crystalline mineral here called zunite. And naturally in that crystal structure, there are units, subunits, that are very similar to our epsilon aluminum 13. The reason I say they're very similar is because we have isomers, and the unit in zunite is actually the alpha isomer. So the alpha isomer is the one that was first discovered with tungsten, because tungsten is larger than aluminum. Aluminum 3+ is a very small ion, and so they can sit kind of closer together and you get this epsilon instead of where the metals sit a little farther apart in the alpha. Now the difference between these is a rotation of the triameric caps. So this is a version of my epsilon with all of my hydroxides and waters shown. Beside it, I have kind of an alternative version where I've taken the waters and the protons off of there. I have grays that are my aluminums. I have reds that are oxygens down here, but this top is showing you one of these trimers, and a 60-degree turn of that cap creates the next isomer. So we could turn one trimer. If I had this one, I could turn a second trimer, I could turn the third one, and by the end, when I turn all 4, that's how we get from one extreme to the other. And so all of these could and do exist, as we'll see. If you take your epsilon and you heat it with calcium and glycine, you can isomerize to your delta after about 2 days, and then a week later, you start to get the gamma version. Why is that important? Well, guess what? In antiperspirants, we have glycine and we have calcium chloride usually. And so we're looking at calcium, glycine, and heat like the environment that you would have with antiperspirant, and we're getting this isomerization. So when I was at UC Davis in my postdoc, we had a collaboration with Colgate-Palmolive, and we were looking at this isomerization. And so we were taking our epsilon aluminum 13, dissolving that into solution. This is aluminum NMR. So here is our full spectrum aluminum NMR. This region down here around 0 is where octahedral aluminums show up. There's not much information we can gain in that region. But down here, between 60 and 80, we have our tetrahedral aluminum. Now there's only one tetrahedral aluminum in this cluster. 12 of them are octahedral. But that one very symmetric aluminum in the middle corresponds to this signal here. And as we heat that, that signal disappears. After one day technically, our delta starts to grow in, which has already been assigned in the literature to this chemical shift. Then we have this very large signal that grows in here. That's another cluster, the aluminum 30, which is 2 of our delta isomers stuck together by 4 extra aluminums in the middle. And then we have our gamma that started to form here after 2 weeks, which is what was predicted by previous literature. And so we were able to watch that. But look, there is a very sharp signal right here that we were able to see. And so this is one of my research students, Kieran, and after I was at SOU, he actually went down and did a summer internship at UC Davis and was able to finish up this project where we actually determined that this very sharp signal, I would not say determined, I would say we predicted that this very sharp signal, based on how sharp it is, I'm sorry, I'm still getting used to the laser pointer and the clicker being 2 different things here. Based on how sharp that signal was, we believe that it was the alpha isomer, because as you rotate these and break the symmetry, your tetrahedral site does not have the same bond angles. It gets distorted, and so you get these broader and broader signals. Those sharp signals in the tetrahedral region, like our epsilon, are only coming from the most symmetric version. And so I looked at the bond angles and found the standard deviation of the bond angles around the tetrahedral site and kind of related that to then the width at half max of these signals, and we were able to see that the only cluster that's known that could have correspond to was that alpha. And so we were able to then publish that we saw that alpha in the signal, and it was the first time outside of the mineral zunite that the alpha isomer with aluminum had been detected. Now, unfortunately, we can't do that at SOU. Our NMR is old, but there is also another reason we can't do it at SOU. At UC Davis, I worked for a geologist. He was in the chemistry program, so we were looking at this from a mineral standpoint, and he had purchased a very special NMR probe that did not have aluminum in it. Aluminum's non-magnetic, it's really light, it's cheap, so most NMR probes have it in there. And so we get this huge background signal covering up all this beautiful data that I was showing you where we can see all those isomers. So at SOU, we can do aluminum NMR, but I can't see any of the beautiful data that I want to see. We also have the problem that there are aluminum clusters that don't even have tetrahedral aluminum. So even if we could see that region, they only have octahedral signals that show up down here, where we have very broad signals, they're all overlapping, and we can't tell one cluster from another. So this kind of gets us into what we're doing at SOU and what I can do with my students. I went to the literature, I had already read these papers, but I went back to the literature and I realized that back in 1989, there was a scientist named Aikit, and he published a series of 12 to 15 parts that he just kept building. It was part 10, part 11, part 12 that he kept publishing. And one of them, he looked at proton NMR of aluminum solutions, and he saw all these signals. And if you read the title of this, aluminum metal monitored at very high magnetic field. Very high magnetic field at that time, maybe you can't read this, was 400. What we have. This one here, 360 megahertz was his very high magnetic field at the time, right? Things have progressed. We have 400 megahertz NMR at SOU. Then in 2006, 10 years before I went and worked for my postdoc advisor at UC Davis, he and his students did proton NMR and found one signal from the epsilon and then measured the exchange rate using VT NMR to figure out how fast that proton on the cluster is coming on and off for geological and weathering purposes. So I thought to myself, we can do proton NMR. Maybe the clusters that only have the octahedral will be visible with our proton NMR when we're looking at these hydroxide bridges. And so maybe I can start to see them in solution when they were blind to us using the aluminum NMR. So in order to do that, the first thing I had to do with my students was synthesize some of these clusters, right? So we took to the literature. Here are some of my students, and the first one we decided to synthesize is the easiest of the clusters to synthesize, and that's this epsilon kagan. So we essentially just dissolve salt in water and adjust the pH. So they take aluminum chloride, they heat it in water to 80 degrees Celsius. They slowly add sodium hydroxide so it doesn't precipitate out too quickly. They let that stir. They dilute it a factor of 12 in all these beakers, so it's super dilute. And it's soluble when it has chloride counterions. But after they dilute it, they add sodium sulfate, and it is insoluble with sulfate. So after about 2 weeks from this very dilute solution, the sides of these beakers are just covered with crystals. We can decant and then scrape those crystals off, and we have this nice cluster that one we can start with. And so my students have done this over the last six years, maybe 7 or 8 times at SOU. We've become pretty good at this. The next cluster we synthesized was the aluminum 30. Now this cluster in the literature, the synthesis is that you make the epsilon, as we said on the last slide, and then you either heat it or you just let it sit for a while. Okay, so what they think is that you have this epsilon, you heat it, and you have a rotation of a cap, you get the delta, and then that's in equilibrium with your delta. Okay, so I thankfully was able to procure a little of this before I left UC Davis, and I was able to bring some solid with me that we could just start with as my students and I were also trying to synthesize this. And so Morgan is my current capstone student. She's working on trying to make more of this. After we have it in solution, which I'll show you how we can determine if it's there or not, we again will use a very dilute solution and crystallize it out with sodium sulfate. So the third cluster that we've decided to synthesize is the flat aluminum 13. Here is the flat aluminum 13. The reason we call it flat is the center 7 are planar, but the outer 6 are up and down and up and down. So it's not really flat, but it's much flatter than our Kagan version. So these are our 2 that have 13 aluminums in them. This one got deprotonated, which is very common. I don't know where that proton got to, but it happens all the time in the samples and in these models. So here I found in the literature 2 different syntheses. One of these my colleagues were doing at U of O while I was working on the gallium clusters, and the other one is just from the literature. And so they're very similar, but one of them is creating the cluster with nitrate counterions, and the other is creating the cluster with chloride counterions, mainly from our starting material, right? We start with aluminum nitrate or aluminum chloride. The other difference in the syntheses is that they're using zinc versus aluminum powder to reduce the solution. So we have a redox reaction here that's creating hydrogen gas bubbling out of the solution, which is making our pH go up because we're losing hydrogen. So we're building hydroxide bridges and forming these clusters. The reason that we hypothesize that this cluster forms instead of the Kagan is because of, instead of adding base and having little micro environments that are very basic, where a tetrahedral aluminum would form, we are very slowly raising the pH through this redox reaction, and so we're not getting any micro environments that are very basic, and no tetrahedral species ever form. We just polymerize the octahedral, monomers that are surrounded by 6 waters that are pretty typical in solution. So both of these syntheses my students have set up, and we're going to talk about them a little bit later in the talk again. We only have shot for 4 of these clusters so far. The 4th one is the aluminum 8. It has a +10 charge. The first publication of this cluster was in 2005, and the synthesis was that they mixed it up, they put it in the refrigerator, and 3 years later they found 1 crystal, and when they did the crystal structure of it, it was something brand new, and they published it, right? not necessarily repeatable. So then comes around 2017, there's a more reproducible, larger yielding synthesis that some of my colleagues and even I am on this paper were able to make and analyze, and then my student at SOU has, oh no, I stepped on the cord. No, I can fix it. Well, maybe I can't fix it. That is very close. That is my computer. And let's just try that again. There we go. Okay, so theoretically, thank you. Theoretically, after 2 days, that it should dissolve. So she's taking aluminum hydroxide, putting it with sulfuric acid. It's supposed to dissolve. But so far we have been very much struggling with this. So that is a to-do to finish a future experiment to get this cluster synthesized. So now that we have a nice little stockpile of 3 of these clusters, the next goal was to start looking at them with proton NMR. So I wanted to look at them in water, right? If these are hydroxide bridges, they could be exchanging with our solvent. They are exchanging with the solvent. And so if I put them in D2O, I was worried that over time they would exchange and I might not be able to see those signals. So I wanted to do all these experiments in water. And so we got NMR tubes with coaxial inserts that we could put our D2O to lock inside, and then our clusters would not be interacting with the D2O. Then we did solvent suppression because we had a huge water signal because of that choice. And so you can see before our solvent suppression, it is very hard to make out any of these signals, but afterwards they become pretty prominent, and all of those signals are corresponding to hydrogens on hydroxide bridges in our clusters. So the other type of experiment that I can do to help confirm which cluster might correspond to these signals is diffusion ordered spectroscopy. So using the NMR, you can do a series of different gradient strength pulses, and then I'll show you on the next slide how it kind of fits it, but what it tells you is the diffusion rate. So as we move down, I know those are small numbers, but as we move down, things are moving quicker. So here's our proton NMR at the top. This is telling us the rate of the species diffusing. And so the faster something diffuses, the smaller it is. And the slower something diffuses with Brownian motion in solution, the larger it is. So we can tell that these signals here are corresponding to a lot. Oh no! You are so right. It's because of the drama. Thank you. Okay, so these signals here correspond to a larger species in solution, and this signal here is a smaller species in solution. And so here's our equation. Diffusion coefficient is inversely proportional here to our radius. That is the solvation sphere, the hydrodynamic radius, right? So from this, we were able to determine that our aluminum 30 has a fingerprint of 5 distinct signals that we're getting from hydroxide bridges, and our epsilon aluminum 13 has 1 signal, which was the one that had previously been seen, and they measured that exchange rate of the proton width. So how does DOSY work? Just a little bit more. Here is a uranium cluster that I studied in my postdoc that I'm just going to use it as an example. This uranium cluster had phosphite bridges. So between the blue uraniums, there are phosphites connecting them. That has a nice phosphorus hydrogen bond. And so the phosphorus was splitting the hydrogen, so we get doublets here. Now, there were free phosphates in solution and phosphates that were bound. And so when you do DOSY, you do a series of proton NMRs at different gradient strengths, and then it uses this equation. The computer fits this for us. I don't do this. I just know how the background works from talking about it enough. But it takes the change in intensity and those gradient strengths, and then your gyromagnetic ratio of whatever element is. And by how quickly these signals decay, that's how it fits the speed that it's diffusing away. And so the things that decay away quickly are our fast-moving small species, and the things that decay away very slowly are our larger, bigger species in solution. And so these little it's a doublet, these little signals are our clusters, and the big ones that decay away quickly would be our free phosphite in solution. And so I'm able to use this experiment to kind of tell our clusters apart, because in solution they have different charges, therefore they have different solvation spheres, and therefore they're diffusing at different rates in solution. All right, so these were the 3 clusters that my students and I were capable of synthesizing so far. And we were able to take these 2, and as I told you, when we crystallized them, they had sulfate counterions. They're not soluble with sulfate counterions, that's how we crystallize them out. And so we had to do a barium metathesis, a double displacement reaction, where we actually grind the powder up with barium chloride, and then we put it in water and shake it, and the barium sulfate stays insoluble, but any of the clusters that are then closer to chlorides dissolve, and you can actually get 100% of your cluster to dissolve using this method. And so after doing that, we were able to get very nice proton NMRs after our solvent suppression that gave us those unique fingerprints that we're using right now to identify which cluster is in solution. Now, our flat cluster, when we dissolve that, it has nitrate or chloride counterions, and that just dissolves nicely. You can dissolve these 2-3 molar in concentration, very strong, which is why they made such good precursors for those thin films. You get a really concentrated aluminum hydroxide solution that's already kind of in the shape to build that extended network. That's why it was working so great. When we dissolved these, I dissolved them with my students at 3 different concentrations, and we didn't see the exact same thing at our different concentrations, which made us a little concerned that it was going to be difficult to figure out our fingerprint region because something, stuff was happening as soon as we were dissolving this in solution. We saw that this large signal corresponded chemical shift-wise to our epsilon. And so initially at low concentrations when we dissolved this, there was epsilon in our sample. And then these 2 signals are pretty prominent in all the spectra, and we hypothesized that these were going to be the 2 signals that were our fingerprint of this flat cluster. But we wanted more evidence of that. And so I had my students who were synthesizing these take aliquots throughout the synthesis so we could maybe watch the cluster forming in the synthesis and then kind of match that to what we were redissolving afterwards to confirm that those 2 signals were hopefully what would correspond to our cluster in solution. And so here they decided not only to do the 2 syntheses, but to mix it up. And so when we had the aluminum chloride and the zinc in one synthesis, they decided to also do aluminum metal and the aluminum chloride. And so they did all 4 variations that we could think of. The bottom is day 0 for each, and then they work up, and we watched it over 5 days. There is a signal in each one of these that I put a little diamond by. Now, because we have a D2O insert, there's a little bit of water in our D2O insert, and depending on what the pH of our water that we're suppressing is, we don't always suppress the little bit of water in the insert. So that signal, now right there, we suppressed it because our signal was also on top of it. But those signals are water. We put a little reference in there, which unfortunately overlapped some of our signals in this one. And so we were able to normalize all of ours. And you see that as these syntheses happen, even like right away for some of them, there's a mess. There's a ton of hydroxide bridges. There's probably dimers, trimers, tetramers, all sorts of things in there that are forming, even though what precipitates out and what has been shown to form from these solutions are those flat clusters. We took one of these that had those 2 signals very predominant, and we ran the DOSE, the diffusion ordered spectroscopy experiment. And we saw that those 2 signals correspond to something larger, diffusing slowly, so most likely our cluster. And from my previous knowledge of working with the gallium version of this, I did NMR and we saw 3 signals. There are 3 types of hydroxides in our aluminum or gallium version of this. There's a mu3 here in the center, and then there's 2 types of mu2s. There's something interior that's kind of holding this interior 7-membered ring together, 6-membered ring around that. And then there's the ones connecting the inside to the outside. What I learned from my work in graduate school on this gallium cluster was that I have to look at it so I get it right. Sorry, it's the little one here. Our interior signal was the most upfield. So here's our interior, and then here's the exterior. So that helps me to decide it makes sense that we would only see 2 here. The reason we're not seeing this 3rd mu3, it would be much farther downfield, and from doing some VT experiments, we learned it's the first to be deprotonated. When I looked at the gallium cluster, we couldn't look at it in water, we had to look at it in DMSO, and so that proton did not deprotonate or interact with solvent, but once we moved that over to water, we titrated water into those samples, and that signal was the first to disappear. So we know that that is the first proton that would disappear, and so we're not seeing that. The cluster is deprotonating, which lowers its charge. If it's a plus 15 charge and it deprotonates the 6 mu3s, it's a much more stable species in solution. And so we're thinking we're seeing 2 signals that correspond to the exterior and interior mu2 hydroxides. And so we've become pretty confident that when we see those 2 signals, it's our flat cluster. The next thing that we wanted to do was go to the literature and mimic an experiment that was happening and see if we could see the same results using proton NMR as they had seen in the literature. And so we know that if we take our epsilon Kagan and we heat it over time, it converts into the 30. And so that's what we wanted to see. And so we took that, before we heated it, it was just mainly this big signal. And over time, after 3 weeks, more small signals grew in. Now those signals, if we zoom in and look at it, correspond to where those 30 signals were. Now, interestingly, there are some other signals in here that we don't know what they are yet, so I'll talk about that in a moment. But I had a student that set this up at a lower concentration as well. So I did it at 1 molar. She has set it up at 0.5. We're watching it again. She has not waited 3 weeks yet, so we don't have that data. But she also saw these interesting signals when she first dissolved it, that there's some sort of impurity that has hydroxide bridges in here. Mystery peaks is what we're calling them. And those mystery peaks I'm very interested in, and I have some ideas of what they might be, and we'll talk about that as we move through this talk more. So the other experiment in the literature that we decided to recreate was looking at our flat cluster. In the literature, it turns out that if you dissolve the flat cluster into water, it converts into epsilon right away, which was what we were seeing in our initial experiment. Our flat cluster was converting from this cluster into this one in solution. And so we can see that with proton NMR. The really cool thing here was we moved up in concentration from 0.1, we went up to 1 molar. We had our flat signals, our epsilon grew in, and then over time, 30 started to appear. So we can see this conversion from one cluster to the other. And that made sense because historically in the literature, it said you get epsilon, and then it comes together, it dimerizes, and you get that 30-mer. But when we move to 2 molar, we're going from flat directly to 30. There is no epsilon forming in between, which was very interesting to us because historically people have always proposed that the mechanism of 30 forming, you had to form epsilon first. And we're seeing maybe a little bit of epsilon, but it's not forming before those 30 are forming. And so that was very interesting to us. And that is something that we would like to tie into a publication that we're putting together. But it's very slow when you're working with undergrads. So the next thing we decided to look at was, okay, well, 30 is forming in these solutions. We know that the Kagan is pretty stable unless you heat it. So let's just look at our 30, our cluster over time, and see what it does. And so here at 1 molar, we dissolved our 30-mer, and 1 week later, it looked pretty much the same. There's a little bit of impurity in there, but the signals didn't change after a week. We looked at it again. Oh, there's a little bit of epsilon I decided to label for you. We looked at that again at 0.1 molar. After a week, all the 30 was gone. And all that's left is our mystery peaks that were the impurity in that previous sample. And so now we know how to make a higher concentration of our mystery signals. My thought is that these signals might be some of our isomers. As you break the symmetry and rotate one of these, you're going to go from one signal, one type of hydroxide bridge, to a few more. And so this could be our delta, that as the 30 is falling apart, we have those delta isomers in solution, maybe even a gamma. And so what we really like to do is say, all right, let's take a dozy of this sample after it's been aged and see if those other signals are diffusing at the same rate, because all of these isomers should be about the same size in solution. And so that's on our to-do list. We want to recreate that solution and then look at those signals and figure out, can we identify what species those are? Okay, so one thing we noticed during all of these experiments was the effect of our counterions. So our aluminum, we looked at those syntheses, and you might have noticed that there was a major difference in chemical shift between the syntheses with the nitrate counterion or the chloride counterion. We also saw with aluminum 30 forming from our epsilon and aluminum 30 forming from our flat, that we see those 5 diagnostic peaks that are similar in height, but the chemical shifts are changing. And the reason for that is there are a lot of interactions in solution between these hydrogens and those counterions. The hydrogens are hydrogen bonding to water, but they're also interacting with those counterions. So depending on where they are on the cluster, if they're pointing in or outwards, they're going to be more solvent-like, or they're going to be more cluster-like, and they're going to have more interaction with those counterions or not. And so we're getting a lot of shifts in chemical, we're getting a lot of changes in chemical shift with just the counterions changing. And this led us to the next set of experiments that I'm going to show you. This next set of experiments, we went from looking at dissolving clusters to dissolving monomer and seeing what clusters naturally self-assemble in solution, okay? So if we look at the clusters that I told you already, our epsilon, our 30, our flat, and our 8, which we haven't been able to synthesize, and we look at their charges versus the number of aluminum atoms, we can get these ratios. Aluminum to counterion, if we're thinking of like a charge of -1 for our counterions, so chloride and nitrate. And we get this variety of ratios. Our monomer is 0.33, our clusters that have the tetrahedral signal are both above 1.5, and then our flat class clusters are 0.8, 0.9, right, as the ratio. So we developed this matrix where we took aluminum hydroxide at different concentrations and an acid, HCl or nitric acid, at different concentrations, and created ratios. So we have this nice 1-to-1 region down the middle, then we have some less than 1, some greater than 1, and then there's the extremes, right, where nothing's going to dissolve here. We're not going to be able to get 1.5 molar aluminum hydroxide in 0.05 HCl. It's just not going to dissolve, but it's part of our matrix.